let us get started with a recap of what we have. Let's get started with a recap of what we have done in the last class. Okay. Now, last class was an important class because we are looking at a problem-solving strategy or a design strategy that's based on modularity, where instead of designing everything at the grassroots level, like the gate level in this case, we are designing something at the modular level. So we design small modules, okay, which are at the gate level, and then we use those modules to design more complex systems. Okay, so this is what we're going to do. We have discussed in the last class as pertaining to the design of a binary adder, right? A circuit that can actually perform arithmetic operations, like addition operations, to be more exact. Okay, so this is the approach that we have taken. Just to recap what we have done, we are trying to design a binary adder, and we want to generalize that. We quickly realized that you can easily design a single bit adder or 2-bit adder uh, using the K-map approach that we have seen before. But really, it's not very useful circuits. What we really need to do is to extend that concept. We want to be able to design an adder that can perform an n-bit operation, n-bit addition operation. Okay, so we want to basically generalize that so that we can actually start adding large numbers together, large binary numbers together. Okay, and towards that, we have realized that we cannot do this at the gate level. Let's pursue what is called the modular approach in designing systems, modular systems. Now, the approach is we'll examine the operation in more detail. Okay, the fundamental level, exactly what is happening, right? And this is what we have done in the last class. So if I look at an n-bit number, an minus 1, an minus 2, so on, ai, some intermediate bit in that n-bit number, so on, a3, a2, a1, a0, and adding that to another n-bit number, bn minus 1, bn minus 2, bi, again the same intermediate position, bit position, b3, b2, b1, and b0. I'm trying to add these two numbers together. Okay. And I see that at every bit position, I'm doing the exact same operation, right? Except for the very first bit where I don't have to consider what the previous carry is. For the second bit, I need to consider what is the carry out from the previous bit position is. When I add A0 to B0, I get some sum called S0 and some carry out called C out, right? C0 in this case. And then in the subsequent bit positions, I'm always adding the individual bits together along with the previous carry. And I get some sum S1 and a carry out from this bit C1 in this case, okay, and so on. So that you're doing the exact same operation at every bit position, and at the intermediate bit position, you'll see that you're adding Ci minus 1 from the Ci minus the I minus 1th bit position. You're adding that to the Ai and Bi to get some Si, okay, and producing another output called Ci, which gets added on to the ith bit, right? Which gets added on to the I plus 1th bit. Okay, and then the process continues. So we have seen that at every bit position, we're doing the exact same operation. So that should give us a clue. Okay, so if I want to design a module that can be replicated, okay, I would probably design a module that can do this operation. And this is exactly what approach we have taken in the last class. And we have actually implemented that module, right? So we have basically, now we see that this particular module, if I want to design that module, this particular module takes in 3 inputs. Ci minus 1 is an input, Ai and Bi, right? And because we are adding those 3 inputs together, 3 bits together, that's Ai, that's Bi. I will call this a full bit adder, a single full bit adder, full bit adder. It's called full bit because I'm also, for this particular design, I'm also considering the previous bit carry. Okay, and that's why it's called the full bit adder. A half bit adder, on the other hand, would not have this. I'm just adding 2 bits and giving out the sum and the carry out, and that's called the half bit adder. All right, that's just a naming convention. And then I produce what is called a CI, the carry out, and SI. Okay, so this is the module I wanted to build. We have actually constructed that module. Now I can easily build it because that's a simple combination circuit. I know what the inputs are. I have 3 inputs, 3 bits. I have 2 outputs, SI and CI. I can easily build that. I can use the K-map approach to build that. No problem with that, right? Okay. Now, and I know the relationship between SI, CI, and my inputs. And we have built that. We have actually done the K-map, and then we have realized what my SI should be. SI. We have seen that SI should be AI exclusive OR BI exclusive OR CI minus 1. So we have seen that in the last class, right? And then CI, my carry out, was given as AI BI plus CI minus 1 times AI exclusive OR BI. Again, if you recall what we have done here, in the original K-map, when we did the simplification using the K-map rules and so on, we got this as AI or BI, right? And then we basically, since we are already computing AI exclusive or BI for my SI, if I can reuse that term, I don't have to have an additional gate there, an additional OR gate there between AI and BI. That would again, help me with the power consumption and other things, making my circuit compact, right? So, and that's exactly what we have done. Even so, by combining them, for my CI, the K-map for CI, by taking the implicants so that I can actually get this expression, AI exclusive or BI, I can reuse this term. It's not going to change the value of this function. So that makes my circuit a little bit more efficient. Okay. So this is where we stopped in the last class. So this is, we have built a single module that can perform this operation. Now, if I want to perform each of these operations, all I have to do is, for an n-bit adder, I have to have n modules of these, right? Basically, because at every bit position, I'm doing the exact same operation. So basically, I need to copy and paste. I construct this module, copy and paste it n times. And then I can perform each of these operations. Okay. All right. So now, let me copy and paste them here. Okay. So that's basically, you have, I have n of these modules. Okay. That's the 8th bit position. And then I have, and so on. Okay. I have n of these 1-bit full adder modules. So these are 1-bit full adder. Okay, I'm just going to say full adder that we just designed. Identical modules, all I've done is just copy and paste them. I have n of those. Now, what are the inputs for the first one? For the first one, again, so these are the inputs, right? For each of these modules, I would have, as inputs, I would have AI. Let me put it this way, actually. For each of this module, I have an input called AI, BI, and just putting the inputs here. Okay. And then CI minus 1 here, CI minus 1 as the input. Same thing here, AI, BI, CI minus 1. Let me just take this out. You know what this is? That's a full adder modules. So I have some space, CI minus 1. That's the input that goes there. Okay, AI, BI. So these are like your, if you can imagine them, like your IC chips, for example. Okay, so I build them. I'm trying to put them together. That's going to be CI minus 1, again AI, BI, CI minus 1, and again that's CI minus 1. Identical modules, I've designed them. What are my outputs? I have an output CSI. Let me call this SI here. SI. Each of my modules will have two outputs, SI and CI, right? That will be my output CI. CI, 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 CI. I have n of these. Okay. Those are my inputs, AI, BI, and CI minus 1. And these are my outputs, SIs. So on the first, for the first bit, I would apply A0 here, B0 here, and I don't have a carry in for the first bit. What should I do then? What should this be attached to? I'm trying to add these two numbers now with my adder. 0. It's perfect. Or I can just ground it, right? The same thing. I'll just ground it. Yeah, and then for the second bit position, I would have as the input A1, B1. What about this CI minus 1? What should I be attaching that to? For this adder, what should this be attaching to? CI minus 1. Where would I get that CI minus 1 input?
C1.
Sorry?
Wouldn't it be into C1?
C1.
Or CI rather.
Okay, from here, right?
Yeah.
Yeah, because this is going to compute your C0. Yes? A0, yeah. B0 plus CI minus 1. In this case, of course, that's 0. AI plus BI. That's going to give you your C0. And here, as you can see here, if I want to add, in this bit position, I would like to add A1 plus B1 along with C0, which is coming from here. Okay? All right. And so on. What about here? Is there a question?
No, my apologies. My audio is still on.
Oh, no worries, no worries. Okay, so here I'll be applying AI, BI, that's my ith position. Okay, maybe I should have shown one more. Maybe here I'll show that. Okay, and here I'll be applying my CI minus 1. Okay, and so on. So this will be my AN minus second bit, BN minus second. Okay, here I'll be applying CN minus third. And of course, I'm going to get here, that's my S0, S1. That's going to be my SI. That's going to be my SN minus second. This is going to produce CN minus 2, which is going to be going to to CI minus 1 input of the last adder. Here I'll be applying AN minus 1, BN minus 1. I'll be getting SN minus 1 here. And as the carry out, last carry out, it's going to be CN minus 1. And that's it. Now I'm able to use these individual adders as individual modules, and now I can generalize the addition operation for any bit number. Okay, so I'm cascading this is a cascaded adder. So these are all the individual adders, the carry out of an adder goes as a carry in to the next bit position. For every bit position, the carry out of one of the previous bit goes in as a carry in to the next bit. So that's how my carry propagates through this adder, and I get the sum. Okay. So what I'm going to do here is just to illustrate this. I'm going to do one more adder here, just to make sure that this is clear. So this is AI, PI, CI minus 1, CI. So that's grounded. So here I'm applying my A0, B0. That's going to provide me with S0. Okay. Then that's my C0 going in to the next bit position. Here I have A1, B1. That's my S1. That's my C1. That's A2, B2. That's my S2. Okay. Just to make sure that it is clear. So the carry out of the individual bit goes in as a carry in for the next bit position. Just like how you do the regular addition process, right? You'll always consider the carry from the previous bit position, add them along with the two individual bits to produce the sum and the carry out that needs to go to the next bit position. That's exactly how we have shown it in this diagram. So that's your n-bit full adder circuit, n-bit full adder, that is made by cascading n single bit adders. Okay. So let me take a pause here and let me see if you have any questions here. Does that make sense, the approach? About the working principle behind the n-bit adder. Are there any questions here? Okay. So that's good. Now what we are going to do now is, since we have it here, I would like you guys to think how I can make this into a subtractor. We have realized an addition operation now. Let me see if you can think about a way to make this into a subtractor. So that now I know also how I can actually make a subtractor circuit. Right? Any ideas there? How do I convert that into a subtractor? The clue lies in the way we do the subtraction operations involving binary numbers. How do we do the subtraction operations?
Could you do the original carry in instead of grounding it, apply a 1?
Okay, that's the first step. Let me do that. Why do you want to do that? You want to apply a 1 there, and what are you going to do there? What's happening then? You're adding, let's say, A to B, and you're adding a 1 to them, right? In this configuration, you're adding A to B and the 1. Again, remember that A is my,
Take the 1's complement of B, wouldn't we?
Sorry, can you repeat that?
For subtraction, we're adding the 2's complement of B.
Yeah,
So
perfect.
we and add a 1.
Yeah. So I take the complements now. See, the complements will actually make sense now. Take the complement. The way we did the subtraction using binary numbers is I take A. If I want to do A minus B operation, I would do this as A plus the 2's complement of B. Right? That's A minus B operation. Or this is, I can also write this as A plus the 1's complement of B, but to get the 2's complement of B, I take the 1's complement of B first and add 1 to that, right? That gives you the 2's complement of B. You already know that. Doesn't make sense? So you take A, you take the 1's complement, you add that to the 1's complement of B, and you add 1 to that. because 1's complement of B plus 1 would give you the 2's complement of B. So now, in other words, you're adding A to the 2's complement of B, which is nothing but you're doing the A minus B operation, right? All right. So this one I can add here. This one I can add here. How do I take the 1's complement of B?
You invert B.
You invert B. That's exactly right. So for every B, for every full adder position, you just invert B's. Again, this circle, this bubble represents inversion. So now you're adding A to the inverted version of B, which is the 1's complement of B, and you're adding 1 to that. So whatever sum you're going to get here, the S is really your subtraction result. Okay. So now you can easily convert an adder to a subtractor operator, subtraction or an adder circuit into a subtractor. Okay, just by that simple modification. All right. Okay. Now this is well and good, but as you can see here, when I do this modification, this particular circuit performs subtraction operation. I cannot again reuse that as an addition operation, right? Because if I want to reuse that, I need to go back to my hardware and change these and make sure that these inverters are not there, and I make sure that this is grounded. So this is good. I know how to perform subtraction. I know how to design a subtractor. I know how to design an adder. But really, I want to reduce the amount of redundancy in my circuit. That means I don't want to have a special circuit constructed that can only perform addition operations and another set of circuit that can perform subtraction operation. Okay. What I really want to do is if I can combine both of these operations into a single piece of hardware. If I can design a hardware that can perform based on what I tell the hardware, based on how I configure the hardware, addition and subtraction operation. Okay. So what I want to design now is an adder slash subtractor. A piece of hardware that can perform both of these operations. Of course, you cannot perform both of these operations at the same time, right? I need to tell the circuit, okay, now at this moment, I would like that circuit to perform addition operation, and maybe at a later time, I can tell the circuit, okay, now you need to perform a subtraction operation. Okay. Now, so let's actually design that. So the 2's complement approach really becomes handy here, right? Now, when we initially described the 2's complement subtraction, it seems like a big chore. You'd have to find the 1's complement and then the 2's complement. Then you have to add. You could have done it directly, A minus B operation, like you do in paper. That could have been done. That would have given you the exact same result. And you're taking these additional steps to do this. But now I hope that makes more sense why we want to go the 2's complement approach. Because this hardware, as you can see, redundancy can be reduced. All right. Now let's design an adder slash subtractor circuit. Now, whenever we want to design, again, so this is a design principle that you need to keep in mind. Okay. Now, whenever I want to design a piece of hardware that is multifunctional, that can perform multiple operations, okay, I need to always come up with a signal, because ultimately you need to be able to tell the circuit, right, what at this particular time, how you would like this circuit to behave and function, right? In our case, in this present case, I have two possibilities for the circuit. At any given instance of time, I can tell the circuit to behave as an adder or behave as a subtractor. Okay. So I need some ways of telling the circuit. And the way I do that is to configure an input called the control input. And I would define control input. I need to somehow come up with a control input concept, incorporate that in my circuit. So that's an additional input. Okay. And I will define it so that for this particular case, I define it so that my control input, if I place a 0 on my control input, that tells the circuit that at that particular time that needs to be configured as an adder. Okay. Likewise, the control input is, if I place a 1 on my control input, that means at that time I would basically configure that circuit or reconfigure that circuit as a subtractor. So this is one way of letting know the circuit or the piece of hardware, okay, how you would like the hardware to be configured at that given instance of time. Now, again, these operations are occurring at the hardware level. Now, what you should be doing moving forward, okay, is since you already have some knowledge, some working knowledge about programming, you must have written some kind of programs, simple programs before, right? And before this class, you may not have really took the time to really delve into the details about what really happens when you write this program on your computer, correspondingly what is happening at the hardware level, right? How is the software communicating with the hardware? So from now on, because we are doing this, we are coming up with these circuits, I would like you to start thinking about that. Okay, corresponding code, how does that influence the hardware? For example, in this case, just to give you some basic idea, let's say you're writing a code. Okay, I would say, do, as part of the code, you do this operation A plus B. Okay. Now, what the hardware is doing once it's compiled, okay, at the hardware level, what the hardware sees it as, when it sees this operation A plus B, the hardware basically puts the control input, puts a 0 on the control input, so that once these numbers are applied to my adder, the adder is configured as an adder, as an addition, as an adder. Okay. On the other hand, if in my code I write A minus B in my code, then at the hardware is basically placing control of 1, so that your adder is now configured as a subtractor. These numbers are applied on my adder. The adder is configured as a subtractor, and you get the subtraction operation through the hardware. Okay. All right. So you should think about this one-to-one correlation between what is occurring at the hardware, the software, the code, and what are the corresponding changes or things happening at the hardware level. Okay. That makes it more interesting, more relevant. Okay. All right. So let's do that. I hope that makes sense. So now let's actually design an adder/subtractor circuit. Okay. So first, again, let me redraw the adder. That's not going to change. Okay. So let's actually, again, because you can easily extrapolate the design to any bit adder. So let's start with a 4-bit adder just to make things simpler, or just to keep things simple for now. Okay. That means I need 4 full bit adders. So that's my first, my second, third, and fourth. Okay. Again, that's my CI minus 1, AI, BI input, CI minus 1, AI, BI, CI minus 1, AI, BI. That's my carry out as the output. CI minus 1 is my input, AI, BI, and then CI, CI, SI, 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 CI. Okay. All right. Now, how do we do this, right? So I need to come up with a way by which I can introduce this control input into my design. Okay. So for that, it's not very intuitive. So let me just actually come up with the solution here. Okay. Now let's examine this operation. If I have an XOR gate, I have an XOR gate. All right. Let me apply something AI here. Let me apply BI. Okay. Okay. If you know what XOR gate is, you have, let's say you have two inputs A and B, my F, and my truth table for XOR gate reads something like this, right? You know this, A and B, F, the output of this XOR gate, 0, 0, 0, 1, 1, 0, 1, 1. Okay. And the XOR gate output is basically 0, 1, 1, 0. So that's the truth table for an XOR gate. All right. Now what I will do is, instead of B, let me call this control, and see what happens. If I look at it from the perspective of control input, let's say this is a control. That means this is my control. Let me call it C, CT, control, okay, CTRL. Now I would like to look at the output from the perspective of this control. So what do you see? If my control is 0, which happens in these two instances, what is happening to my F? So my control is 0 in these two instances. My control is 0. My F, what can you say about F in terms of A, the input, other input A? What can you say about F, the output of this XOR gate, as a function of A? If my control is 0, if I fix my control to be 0, what can you say about F in terms of A? Same as A. Perfect. So if my control is 0, let me put that control is 0, implies my F equals A. What about if my control is 1? What can you say about F in terms of A? This happens here, these two cases. My control is 1. What can you say about F in terms of A? F is A prime. Perfect. My F is A prime. In other words, I can programmatically change my A. I can invert A. If I can, let me put it this way. By using this scheme, using XOR gate and the control input, I can invert A or not invert A based on what I apply on my control input, right? So what that means is, if I want to configure this as an adder / subtractor circuit, which can perform A minus B operation, I would apply my A0 here, A1, A2, A3. It's a 4-bit adder. Okay. Now, any ideas on how to complete the circuit so that this can perform addition operation or subtraction operation? Where if I want to add, I would basically I would not invert B's, right? And I want to make sure that this is 0. And basically I add A to B. If I want to subtract, that means I have to invert B's and then place a 1 here, and that would be configured as a subtractor. Okay, any ideas there? You had the clue there. I gave you the clue. How do I complete this circuit so that this can perform both an addition operation as well as a subtraction operation at different times? What can we do for B's? Any ideas from the class? Brandon, what do you think? Can we do something here? How do I introduce my control input? So that based on the control input, I can either invert B or not invert B. That's the clue. So based on the control input, I should be able to invert B or not invert B.
Invert?
Yeah, how do I do that? How do I do that programmatically? By connecting B to the input. Okay, so the clue lies here. So what I will do is, instead of directly attaching B's, I would basically use an XOR gate in between. Okay, where one of the input to the B's would be my BI. In this case, that's going to be B0, B1, B2, B3. Okay. The other input would be the control. Okay. So that's the control. And this control is going to be, this is the same control applied to all of the other inputs. Apply the same control. Okay. And apply it to my Ci-1, my first adder. And I call that the control. Okay. All right. The same control. Now, my circuit is complete. Oh, wait a minute, not really, because I still have to do these connections, right? We do have them. So that's your C3, S3. We don't need these anymore. And now I have basically completed my circuit. That's my S2, S1, and S0. So now this particular circuit would function both as an adder / subtractor. So when I apply control of 0, basically that's 0, that's 0. And we have already seen that when my control is 0, this is an XOR gate. My output here is nothing but B0. Right? Whatever I applied here, that goes in without being inverted. So I'm applying A for this particular adder. I'm applying A and B with a C in of 0 for the first adder, and that's basically performing your addition operation. If I want to perform this subtraction operation, then I apply a 1 here, control input as 1. When I apply control input of 1, I'm applying a 1 here, a 1 here, and we've already seen, right, when the control input is 1, then my output is the inverted version of the other input. In this case, that's B0. So my B0 is going in as B0 prime, B1 is going in as B1 prime, and so on. So each of my B's are inverted here, being applied to my adders. So I'm adding A to the inverted version of B along with 1, and I'm basically performing the subtraction operation. A, so that basically that's your A plus 2's complement of B, that gives you a subtractor. The same circuit, I can configure this at different times as an adder or a subtractor, just based on what I apply on the control input. Okay. All right. Let me just take a pause here and let me see if you have any questions here on the design approach. This is very important that you get it. The control inputs are, you will be seeing that more and more, especially when you're trying to design a circuit that is multifunctional. where you want the same circuit to perform multiple operations, then you will have to incorporate a control input into your circuit design. Okay, and then you would encode your control input so that if you want 4 different operations from the same circuit, then you would have 2 bits to be encoded. So 0 0 would be corresponding to one operation, 0 1 would be corresponding to a different operation, 1 0 a different operation, 1 1 a different operation, and so on and so forth. Okay, so that's how your control inputs are come into the picture, and that's how you would configure your control input. This is just one example of that. Any questions on this? Does that make sense? Does that make any conceptual sense? Okay, very good. All right, so that's well and good. So as we have seen, this is just a 4-bit adder, but if I want to make it into an 8-bit adder, what do? Let's say I have 2 4-bit adders available to me, and I want to make it into an 8-bit adder. How would I do this? So let me call this 4-bit adder. So I have 2 of these available. And I want to make them into an 8-bit adder. I will just cascade them together, right? So the C out, this C out goes in as the C into the next 4-bit adder, and that's your final C out. You ground this, and that's it. So now you have, of course, you apply the first 4 bits here, and the next 4 bits here for the inputs, right? And that makes it into an 8-bit adder. Again, I show a single arrow, but you can imagine that this contains this contains 4 bits of each. As a matter of fact, this is a convention we will use. So when I say an arrow like this and slash 0 to 3, let's say I call this A 0 to 3, what that means is I have basically 4 arrows going in. A0, A1, A2, A3. Because it just makes it very cumbersome, I can just show that with just one arrow with this slash. Okay. All right. So that's how I would basically make using 2 4-bit adders. I can combine them to make it an 8-bit adder. Likewise, I can just keep cascading them together, and I can make more and larger adder. Okay. With this approach. All right. Now, but the problem is, I can do that, which is fine. There's nothing wrong in that. But I cannot just keep doing that, because eventually I land into a problem when I keep doing that. What I would like you to do is look at this circuit, look at how this addition operation works, how this hardware actually works. And I would like you to think about what kind of problems you may be encountering when I just keep on adding modules to it, keep on cascading these into larger and larger circuit to perform, large bit addition operation. What kind of problems do you think we will encounter doing that? Do you see any issues with this design? Lag, okay, very good. Can you elaborate on that? Why are we going to see a lag? That's exactly right. So my carry outs are not produced instantaneously, right? For example, here, if I want to produce the right sum here for this last module, that means I need to have the right carry in here, right? If I have the right carry in here, then I'm adding A3, B3, which are applied, which are directly going in to this particular, along with this particular carry in, and then I get my sum, the right sum and the right carry out. However, to get this right carry out, I need to be able to do this operation first, right? Then again, this particular module would require the right C in here. And this right C in is computed by this module. So I need to wait until this module completes the computation to find the right C in. And again, this module depends on the C in from this module. So when I keep on adding modules, My carry ins have to basically propagate through these modules, right? So and of course, my circuits do take time to compute. Of course, for a simple circuit, for an individual adder, the lag time may not be large, but it's not zero, right? And so you have some infinitesimal lag here for each module, and that lag basically gets added up. As I add more and more modules together, that lag gets added up, and that could be a problem later on. Okay, although if I wait long enough, eventually my sum will settle down. I may be getting some sums as these computations happen, but eventually if I wait long enough, after I made sure that all the carry, I get the right carry in here, propagated through all the stages, I get the right carry in here, then I will be getting the right sum. So my sum will not be the right sum immediately, but I have to wait some amount of time before I can my sum basically settles down into a steady value. So that's an issue that we have to look into, that we have to remember that the circuit is not perfect. It's helpful, it's not perfect. We do have some limitations to the circuit, and there are some remedies to that. There are some alternate designs for the adder, which you have in your textbook, but we're not going to really cover that. And so that's because that's not a very modular approach. That's but that is there. There are ways that you can do design adders where you can predict the carry, and that's actually a carry look ahead adder design. If you're interested, you should basically look at the design in the textbook. But this is a more modular approach, and for most cases, especially for when your adder size is not large enough, then this should actually work. Okay. All right. So that's good. So we have designed this as a first example, our adder / subtractor circuit using simple modules. The simple modules, again, once I design them, I don't have to really show the internal workings of each module, because I know, as long as I've shown it for one circuit, for one module, I don't really have to repeat that all the time. So by this convention, I know exactly what I'm trying to present. Okay. So that's good. So let's move on. Any other question before we move on to the next design? Okay, so that's good. Now we have done the binary adder that can take two binary bits together, two binary numbers together. They can add and provide me with an answer, which is a binary answer, right? Now, oftentimes, let's say you're trying to design a calculator. You want to design a calculator that can perform not binary operation, but you want to input information as decimal information, right? Because most of the time we are working with decimal numbers, right? If I want to design a simple calculator, then it takes in decimal numbers, performs the addition operation, produces some result, that decimal result, and displays that result as a decimal number as well. So we want to do this, right? So now let's actually try to design a decimal adder. So now we have designed a binary adder. Let's start designing a decimal adder. So that will be our next example of modular design. So we are kind of getting in depth there. So now we want to design a decimal adder. As a matter of fact, we are trying to design an actual calculator that can actually perform simple addition operations between two decimal numbers. Okay, and what I would really like you to do, again, this is not a required aspect of the class, but it will be a fun exercise for you. If you can, as part of your lab, and you're working in your ELE 250 lab, if you can actually design a simple calculator based on what we have covered in the class, and see if that works. Okay, that will be a nice application of what the concepts you have learned into actually designing a real system. All right, so let's do that. Let's but before that, let's actually understand what we are trying to do here. We are trying to design a calculator, right? So you have these individual buttons. So you need to have some kind of an interface. Okay, so that's your input device, your keyboard, where you're punching in numbers. Okay, and you need to have some kind of a decoder here, or I would say encoder there. Maybe I can just put that as an encoder. So your buttons are connected to the encoder, and so those are your decimal digits. So let's say I'm just showing some numbers. Now you can imagine you have 1 through 9 on your keypad. You have some kind of an encoder there that encodes each of my decimal digit into what is called the binary coded decimal value, right? So when I press, let's say 6, that comes out as its corresponding binary coded decimal value. Because again, your hardware itself that you're going to design, that's your BCD adder. Okay, I don't think we have enough space here. This is what you're going to design, a binary coded decimal adder. Okay. All right. And let's say this is a 2-digit, 3-digit decimal adder. Just keep things simple for now. 3-digit decimal adder, that means you're adding, 2 3-digit numbers together. That's the maximum you can add. But of course, if you know how to design a 3-digit decimal adder, you should be able to design, just like what we've seen for the binary adder, but just by cascading, you should be able to extrapolate that into an n-digit decimal adder as well, easily. So for now, let's just consider 3 digits. Okay, what it means is, okay, let me put it this way: 3 digits, right? So I need to have 3 of those adders. Each adder adding 2 digits together. Okay. All right. So from here, I have the encoding. Each of my digit is converted into a 4-bit binary coded decimal value, right? And likewise, I have the other digit coming in as 4-bit binary value, and so on. Okay, I'm not going to show it for everything, but at least, So let's actually consider this one digit adder. That's your BCD adder, BCD 1-digit adder. So it's trying to add 2 digits together, 2 decimal digits together. My decimal digits are in the form of binary coded decimal value. So this encoder basically converts them into binary coded decimal value and adds them together and produces a sum. Okay, how many bits should I have for the sum? It's a binary coded decimal sum. How many bits? 8. Why would I have 8? Okay, let's 4. Okay, let's take an example to illustrate that. Let's say I'm trying to add two digits together using this adder. Okay, that means my 7 is encoded as B0111, right? That's the binary coded decimal value for 7. My 6 is encoded as 0, 1, 1, 0. Okay. 7 plus 6 is what? 7 plus 6 is 13. And the corresponding binary coded decimal value should be 0, 0, 1, 1 with a carry out of 1, right? Because the binary coded decimal value corresponding to this is 3. That's the carry out, which is 1. This is the carry out in this case. This is the carry out in this case. So my sum is 13. 13. So 13 is expressed as 1 followed by 3, 0, 0, 1, 1. And when we are working with binary coded decimal values, right? Does that make sense? In other words, I would have 4 outputs, 1, 2, 3, 4, because my sum is also binary coded decimal value. That's my sum. This is the binary coded decimal sum. Okay. And this should also have a carry out, which would be going into the next one, right? Carry out. Whether you're doing a binary addition between two binary numbers, or whether you're doing a decimal addition between two decimal digits, the carry out should always be either a 1 or a 0. You can check it, right? The carry out cannot be larger than 1, whether it's decimal or whether it's any base. When you're trying to add two digits together, the carry out is always going to be 1 or 0. Okay, so I can still represent that with single output. Okay. All right, that's my BCD sum. And I would now I need to have, for each of my binary coded decimal adder, I need to also have a 7-segment display decoder, because ultimately we want to display the sum as a decimal digit, right? So now that's a 7-segment display decoder. We know how to design that. And that will basically convert your binary coded decimal sum into your proper format, right? Into a proper decimal digit format. And you will have, for a 3-digit adder, you'll have 3 of these decimal decoders, or 7-segment display decoders, to convert your individual digits, binary coded decimal digit sums, into the corresponding decimal displays. Okay. Now, do you see the overall architecture? Are there any questions before we move forward to actually building one? Because ultimately, if I can build this one, I should be able to copy and paste this here, copy and paste this here, and I get a 3-digit decimal adder. If I want to make it n-digit, all I have to do is just copy and paste it n times. Now I have an n-digit decimal adder. Copy and paste each of these modules, because again, for an n digit, I would have n digits to display. So I would have n 7-segment displays and so on. Okay. The overall architecture, does that make sense? Let's go one step by one step, slowly, and because this is a little bit more involved than what we have seen before. So I would like to make sure that you're following through as we are moving along. Any questions on this? Does that make sense? So Fabian, do you have any questions? Yeah, James.
Can you hear me? Hello?
I can hear you.
Question is, for a calculator, how would the lag be prevented or offset?
Oh, for the calculator, how the lag be prevented or offset. We are not too much worried for it, because in today's, the way how our circuits are designed and at what clock speed we are running them, you don't have to worry too much about the lag. The lag is insignificant. It's at least for the um, kind of computation we are doing at this time. I'm not too worried about that. Does that make sense? Okay. But again, the reason why I want to go through this architecture in entirety is I want to see at least some of you actually work on this and actually create a calculator in the lab that can actually work from scratch, right? It's a fun exercise. Okay. Now, what I want to design now is we have already designed this. We know how it works. We know that. What I'm going to do now is to design this part, this module. I will consider this as a module now. I want to design this module so that I can basically copy and paste it. Okay, so let's do that. Let's look at the level 0 design for this. So I know exactly what my inputs are, what my outputs are, and then we'll start from that process. So I'll design that module first, and then followed by that I will, followed by that I would basically copy and paste that modules to form an n-digit adder circuit. All right, so that's my level 0. That's going to be your binary coded decimal adder, BCD adder, a single digit BCD adder. Okay. Now, what are my inputs and what are the outputs? How many inputs do I have? What is this particular adder trying to do? It's trying to add two binary coded decimal values together along with the previous carry, right? Along with the previous carry, producing, just like what we have seen for the binary adder module, producing an output, the sum, output sum, and output carry out. So I have 2 digits coming in. That's your digit 1. Let me call that AI. That's your digit BI. But what you're actually applying, because that's a decimal digit being converted into a binary coded decimal value, that means I have A3, A2, A1, A0 being added to, that's the binary coded decimal value of this corresponding digit being added to B3, B2, B1, B0. Again, that's the corresponding binary coded decimal value of digit BI. And I need to add that to my previous carry, call that CI minus 1, producing me a sum, let me call the carry out first. Let me producing me a carry out CI and the binary coded decimal sum S3, S2, S1, S0, which is really the sum SI. This is the decimal sum, decimal digit sum. Displayed as a decimal digit through my 7-segment display. Okay. So that's my level 0 diagram. I want to design this where I have 9 inputs coming in, 5 outputs going out from the system. Now I already see the problem. In the previous case, when I want to design a binary adder, it was much simpler, right? My single module had 3 inputs, 2 outputs, much simpler. I can actually use the K-map approach and design it without any problem. But here, I have a big problem. Even to design this module, a single module, it's pretty complicated. I have nine outputs, 9 inputs. That means if I want to design it through the K-map approach, I should have 2 power 9 cell K-map. Just not a good way to do it, right? So what should we do then? What we should do then is to see if we can apply existing modules and design our adder, single bit adder. So this is the module. We are trying to design a module, but we'll design this module using existing modules. Otherwise, this is going to be too complicated, as you can see. If I want to design it at the base, at the fundamental level, using the fundamental gates, it's going to be already complicated. All right. All right. So let's examine the operation itself. Okay. I hope that this makes sense. So let me take this out. So now let's examine the BCD addition operation itself and see if we can get some clues from that. Okay. Now, let's say I'm adding 2 digits together, 3 and 2. The corresponding binary coded decimal value for these are going to be 0, 0, 1, 1 for 3, 0, 0, 1, 0 for 2. I'm adding them together. And what do I get? I get 5, right? Supposed to get 5. And here I get 0. 1 plus 1 is 1, 0. That's going to be 0. I'm sorry. That's going to be 1. 1 plus 1, 1 plus 0 is 1. That's 1. That's 1. That's 0. Okay. So that's 0, 1, 0, 1, which is 5. And that is a BCD value. That's the correct BCD value. That's the correct binary coded decimal value. Okay. All right. Now, the reason why I wanted to do this, what can you tell? What do you see a hint here? When I'm adding these 2 digits together, the corresponding binary coded decimal values together, what am I doing here? I'm basically adding them together as I could as well use a 4-bit binary adder. We know exactly how to design a 4-bit binary adder now, right? If I place these inputs on my 4-bit binary adder, I will be getting this sum from the binary adder, right? Do you see that? So the hint is I may be able to use a 4-bit binary adder instead of designing an entirely new adder. Okay, I may be able to use a 4-bit binary adder. Okay, where I apply my BCD digits here. That's my BCD digit 1, BCD digit 2, along with the previous carry, and I get my sum. Again, my sum is going to be in binary format and a carry out. So when I apply, in this case, for this particular example, when I apply 0, 0, 1, 1 here, and then 0, 0, 1, 0 here, the sum I'm going to get is 0, 1, 0, 1, and no carry out, and that's the right BCD sum. So there may be a way by which I can basically use existing modules, in this case 4-bit binary adders, to construct my BCD adder. So that's the clue we need to see. Instead of trying to design an entirely brand new circuit at the gate level, I may be able to use the existing 4-bit binary adders that we know how to design. Okay, we have already shown them. We have already designed them, so we know how to design them. Okay. Now, will it work all the time? That's the next question, right? This worked in this particular case, but what about a different case. Let's see. In this case, let's say I'm applying a different input and see if this is, we may be able to actually use this. Let's say in this case, I'm adding 7 to 5. The decimal digit 7 to decimal digit 5. I know the answer, which is 12. Right? That means 1 should be my carry out, 2 should be the sum. Right? The corresponding binary coded decimal value for 7 is 0, 1, 1, 1. Corresponding binary coded decimal value for 5 is 0, 1, 0, 1. I'm adding them together. And what do I get? I get 1 plus 1 is 0, 1, 0. That's 1 plus 1, 1, 0. 1 plus 1 plus 1 is 1, 1, 1. Now, what can you say about the sum? In other words, when I apply it here, that's my first BCD number. Let's say that's 7, 0, 1, 1, 1. Corresponds to the digit 7. This corresponds to the digit 5, which is 0, 1, 0, 1. This corresponds to digit 5. I get a sum 1, 1, 0, 0, carry out of 0. Okay. All right. Do you see a problem here? Am I getting the right sum or the sum I need by using this 4-bit binary array directly? What can you say? What can you see here? The sum I'm supposed to get is 12. What is this? This is 12, no doubt. This is binary. This is basically 12. The value of this is 12, but is it in the right binary coded decimal format? What should be the right binary coded decimal format for that particular number, for that particular sum? Okay, the sum would have been, for that sum should have been 0, 0, 1, 0, because my 2 should be represented as 0, 0, 1, 0. That's the binary coded decimal representation of 2. And then that the carry out should have been 1. There should have been a carry out here from this position, a 1. So this particular sum, oh, wait a minute, sorry, followed by 0, 0, 1, 0. So this would have been the right sum. Or right, I would say, right binary coded decimal sum. This is the binary sum, which is correct because that is 12. If the value of that is 12, but it's not in the right format. It's not in the binary coded decimal format. We need to do some additional adjustment by which we can get the right binary coded decimal format. Okay. All right. So I hope that's clear. And in the next class, we'll complete the design of the binary coded decimal sum, the binary coded decimal adder, which is going to be on Tuesday. Okay. All right. So any question before we conclude our class session today? Does that make sense? This is very important. I hope you won't forget it over the weekend. But this is important, that when I apply directly to a binary adder, my binary coded decimal values, sometimes my sum is correct or in the right format, in the right binary coded decimal format. Sometimes, as in this case, my sum is not in the right format. I need to do some adjustments here to get the sum into the right format. And in the next class, we'll actually look at what kind of adjustments we can do and when should we be doing those adjustments to get the right BCD sum, the binary coded decimal format sum. Okay. All right. So let me stop the recording here.